All right, here's the next one. This is on the inclined plane. You'll see the formula's pretty similar to what we've been dealing with already. On the next slide here, you'll see an example of one. It gives you pretty much the same information. That's just theta to measure the angle, but we don't even need the angle for this. What we need is an effort force that's pulling some sort of load force up a ramp, a load force that's being pulled down by gravity. We need a length of the ramp, and we need a height of the ramp. Which basically makes a triangle. Would make you think that there's some trigonometry that's going to occur here, but there's really not. All we need is a length and a height. If you remember from the lever is load force times load distance equals effort force times effort distance, except now, instead of a load distance, we have a height. We're trying to move the load. Instead of an effort distance, we have a length of a ramp. And I prefer to use an uppercase L rather than a cursive L for that length. So, number one, a worker can only push with a force of 75 newtons. If that's how much force you can push with, then you should not be hired as a worker. It's not very much force. The weight, the load force to be lifted is 256 newtons. Trying to get it up onto a platform that's 1.6 meters high. How can this worker get that thing up to that 1.6 meter height? How long a ramp would be needed? So it's just load force times the height equals the effort force times the length. The load force is 256 newtons. The height is 1.6 meters. The effort force that you're able to lift with is 75 newtons, and we want to figure out what length of ramp is required. You just go 256 times 1.6 divided by 75, and that equals 5.5. The length of ramp is 5.5 meters. In order to make that happen, it's that easy. Math works a lot like the other machines that we've done so far. Number two, what effort force is needed to push this particular box up the ramp? I'm going to change that mass and take it right out, and I'm just going to say that the load force is 500 newtons just to get this thing working, and we don't need the mass then. This time we've got 65 centimeters and 2.5 meters. That can be an issue. Because it doesn't matter what these units are, but they have to be the same. So either you got to convert the meters to centimeters or the centimeters to meters. And in this case, my preference is going to be to turn that into 250 centimeters. 250 centimeters. For no reason in particular, we could just as easily have turned that to 0.65 meters on the height, but I'm just choosing to do it this way. And now I can proceed. So it's load force, 500 newtons, times the load distance, or in this case it's the height, 65 centimeters, is equal to the effort force times the length of ramp, which is 250 centimeters. The units just have to be the same. And I'm going to type in 500 times 65 divided by 250. Gives me 130 newtons. Effort force equals 130 newtons. And that's that one. However, if the actual force you need to move the box up the ramp is 112 newtons, actually let's change that to make it higher. That's the point of this particular part here. Let's change the 112 to be 200 newtons. And we want to figure out what the AMA and the efficiency are. All right, so AMA is equal to load force over effort force. So the load force, 500 newtons. The effort force, the actual effort force is that 200 newtons. In a perfect world, if there was no friction, we got 130 newtons. So 500 divided by 200 newtons is 2.5 for our actual mechanical advantage. To get percent efficiency, we also need the ideal mechanical advantage, which is usually it's your your effort distance over your load distance, but I'm just going to write it in the top right here because I don't think we've seen it yet. The IMA for this is going to be length over height because that's what we've substituted in for those distances for this particular machine. So that's going to be 250 centimeters divided by 65 centimeters. So I go 250 divided by 65, and it gives me 3.8. So for my percent efficiency, see if I can write that a little nicer. My percent efficiency, it's going to be equal to the AMA divided by the IMA times 100. So that's 2.5 divided by 3.8 times 100. I'll just squeeze that into the bottom here, 2.5 divided by 3.8 times 100, and that gives me 66%. 66% efficient, that machine. Now, the reason we're squeezing percent efficiency into this machine is because this is the first machine that we see that friction really is a major factor. Unless this box is on wheels or something like that, something to reduce friction, then friction is going to be a major issue with the inclined plane as a machine compared to the wheel and axle and compared to the levers. So let's move on from there. I think we have a summary slide here. Summary for the inclined plane. The length is always greater than the height, right? It is a triangle after all, right? If we got a height here and a length here, well, you just don't have an inclined plane if the height is greater than the length of the ramp. That's just not going to work for you. So that means the mechanical advantage, or at least the IMA, should always be greater than 1. I suppose if there's enough friction that you could have a situation where the mechanical advantage falls below 1. But then you're not using the ramp properly. The ramp is supposed to make getting things up a height easier. That's why we use staircases, and that's why ladders are on an incline and stuff like that. So that's it for this one. Again, there'll be a couple of questions on your assessment next week on this. So go back through this and make sure you can do those calculations. All right, that's it for now.